In this video, we're going to look at the orbital view of forming pi bonds. So, just getting right into it. So, remember that when we're looking at the orbital view of things, we're looking at how orbitals can actually overlap to give rise to the covalent bonds and enable the sharing of electrons. So the orbital view of pi bonding is no different in that regard. We're looking at ways to overlap orbitals to share electrons. Now, what's different in this case that I alluded to before is that pi orbitals use non-hybridized atomic orbitals. And the non-hybridized atomic orbitals that they use are p orbitals. So because they use p orbitals and no s orbitals, we're going to move away from sigma bonds, which is the Greek letter s for s orbital always being involved in our sigma bonds, to pi orbitals, which always use non-hybridized pi bonds. Well, I mean, they can use some other types of orbitals, but for our purposes, they're going to use p orbitals. So pi orbitals not only use non-hybridized atomic orbitals, the p orbitals, but overlap occurs. So that's kind of point one, is we're going to use non-hybridized atomic p orbitals. Point number two is overlap occurs in a side to side manner. It's actually a bit awkward, but we can go ahead and try to draw it anyway. So the orbital view looks like this. Okay, we're going to take, let's say we have two carbon atoms. This gets really awkward. The p orbital's like right in between the, right over the C, because it's the nucleus. The nucleus is in the center where the two lobes connect. So this left orbital here should be a little bit more symmetric. I can do better. I can do better. Excuse me. I will do better. No try, only do. Okay. Whatever. So I guess I didn't do. So imagine those two orbitals are perfectly drawn, symmetric, dumbbell-shaped orbitals. Each of them has one electron. We desperately want to form a covalent bond where two electrons are shared across two atoms. That gets us one step closer to our octet. So we're going to let overlap occur. Now, overlap is going to be awkward. We cannot swing down and do head-to-head overlap. That's already occurring with the s orbital that's involved here. So, right, we already have an s orbital with little lobes. Just the picture gets messy. So let's ignore that. But that reminds us that we can't just flip those p orbitals down to let them do head-to-head overlap. Instead, what we're going to do is let them kind of squeeze around the sigma bond by leaning into each other. And when they lean into each other, there's partial overlap that occurs on the side of the lobes of the symmetric non-hybridized p orbitals, where the electrons can now exist. And it's not just the overlapped region, they can exist throughout the whole thing. So overlap occurs, but it's side to side. And it was awkward to draw. It's even more awkward if your electron's trying to be shared across these things. So side to side overlap is weaker than head to head overlap. How about this? Is less efficient, because I want to use the word weaker for something else. So it's less efficient than head-to-head. It's awkward. So if it's less efficient, what that means is that pi bonds are weaker than sigma bonds. And that's all comes down to the orbital overlap. we have these non-hybridized p orbitals trying desperately to get like a smidgen of overlap to share their electrons. It's not as efficient. The bond is not as strong. So less efficient, the pi bonds are weaker than the sigma bonds. Okay, what this means is that pi bonds are weaker than sigma bonds. But this comes with a huge caveat. But atoms that are double bonded are more strongly held together than those with only one bond. Okay, so that is if we're looking at a system like this versus this, carbon-oxygen double bond versus a carbon-oxygen single bond, the combination of 1 sigma plus 1 pi is greater than 1 sigma plus 0 pi. So if you have a pi bond, it's going to strengthen how tightly held the atoms are, and they'll actually decrease in bond distance to reflect that. It's just that that additional bond wasn't as strong as the first. Okay, if you look at a pi bond by itself, which you can't have, you always have at least 1 sigma bond. But if you just look at the strength of a pi bond versus the strength of a sigma bond, the pi bond is much weaker than the sigma bond. And that's important because when we do actual chemical reactions, they tend to prefer to go on and happen at pi bonds more so than sigma bonds. The only sigma bonds that can really react preferentially to a pi bond are those on acidic hydrogens or with that are heavily distorted by differences in electronegativity. So they're stronger. Now what we can do is we can actually look at the entire orbital view. Let's do the orbital view of this molecule now. This molecule is called ethene. Let's just pick it as an example. So the orbital view of this molecule's bonds. What you want to do if you want to break down a molecule in terms of its bonding network is to shift focus and separate and focus on the sigma bonds separate from the pi bonds. So the sigma bonding network for this particular molecule is just a bunch of head-to-head overlaps between the two C's. We have H here, and we have H here, and then little lobe to big lobe here, little lobe to big lobe here, and H, and then H. Okay, so that's my sigma bonding network, the arrangement of head-to-head overlaps that allows for our molecule to form. Now, what do we notice about this? Well, if you recall, anytime we have 3 things attached to a central atom, not the number of bonds, but the number of things where things are atoms or electrons, or excuse me, atoms or lone pairs, then we count those things, and if they're 3, then we need an sp2 hybridized orbitals to form our sigma bonding network. Okay, now what about the pi bonding network? Well, pi bonding network only impacts the carbon atoms. So we're going to draw, and you know what, let's give them some lean. Let's make them lean into each other. We have our carbon, dumbbell shape with a lean, dumbbell shape with a lean, top dumbbell, bottom dumbbell with a lean. And I don't know how to make these things look prettier. It's an awkward bond to draw. It's an even awkward bond to pull off. Maybe you just want to draw normal dumbbell shaped orbitals and just let them show these lines to interact to show that we're doing the side to side interaction or overlap. That is fine. Okay, so we've got our pi bonding network, our pi bonding orbitals, and our sigma bonding network, our sigma bonding orbitals. This is a nice kind of depiction to do at least a few times, not for every molecule by any means, but it's a nice depiction to do once because it brings up an important point that pi bonds are perpendicular, that is to say 90 degrees, from sigma bonds. Okay? So when we had everything in our sigma bonding network sort of flat against the piece of paper, I don't know how to, it's flat against the piece of paper, it turns out, put my iPad on the screen here, turns out the pi bonds were actually perpendicular or sticking out of the piece of paper, or the screen in this case, to form the pi bonding network. The pi bonds were perpendicular to all of those hybridized orbitals involved in the sigma bonds. Now, what that means is that if it's perpendicular for that one pi bond, when you have two pi bonds, it gets to be incredibly awkward. So triple bonds, if we have triple bonds, and we'll do a similar molecule where we've got just two carbon atoms attached to each other and the requisite number of hydrogens. Sigma bonds look like this. Now, if you recall from the previous movie, when we have two things attached, everything is sp hybridized. I could probably draw these hybrid orbitals to reflect that a little bit more by having, well, no, they're fine. Hybrid orbitals are fine. Let's just draw a big lobe, a little lobe, a fish, okay? Not worry about it any more than that. So there's my sigma bonds. Now my pi bonds are going to be perpendicular to those sigma bonds that form a linear geometry. So both of those carbon atoms have a linear molecular geometry across the three atoms. An HCC connection in either case for either carbon is linear. Okay, so pi bonding network is a little bit tough to draw for one of them, but the other one's not too bad. The pi bond, we're going to have one of the pi bonds form, and it's going to be perfectly perpendicular. If the linear triple bond is moving across the x-axis, then one of the pi bonds is going to be perpendicular along and is going to be parallel to the y-axis. So sticking straight up and straight down are going to be the non-hybridized p orbitals that form one of the pi bonds. And so again, the x-axis is our sigma bond, the y-axis is one of the pi bonds, and the z-axis so maybe I'll have yellow for this first pi bond, and then this color for the second pi bond. So it gets to be a pretty messy drawing, and it's aided a little bit by colors. But hopefully you can at least see that as we add additional pi bonds to a system, they must be perpendicular to that original S sigma bonding system, okay? It turns out that it gets more and more awkward. The second pi bond is weaker, has a weaker overlap, is harder to pull off than the first pi bond. And both pi bonds are weaker than the sigma bond. So sigma bond always beats a pi bond, and a second pi bond is worse than the first pi bond. But the combination of one sigma bond by itself is weaker than the combination of a sigma bond plus a pi bond, that's a double bond, which is weaker yet from a sigma bond plus two pi bonds. Each additional pi bond, as they get more and more weaker, they still provide an overall increased strength connecting the two atoms together. Okay, so that was an orbital view of pi bonds. Really important to kind of see that at least once, and it's definitely important to carry forward as you think about how these things are trying to fit, these orbitals are trying to fit to make sure that the electrons can be properly shared. Take away from this that triple bonds are inherently sort of, well, at least one of the pi bonds is weak. And if it's weak, that means it's reactive. And triple bonded systems do a lot of really interesting reactions, some of which double bonds can do some of, but not as much. And then single bonds can't get anywhere near what the pi bonded systems can do unless there's incredible distortion due to differences in electronegativity or a huge difference in atomic size, like carbon being bonded to bromine. Anyway, that'll do it for this lecture.